So back in late 2020, a group of researchers at Google dropped a paper with this kind of weird title. It sounds more like a riddle than a scientific paper, right? But this paper, well, it completely changed how we build AI that can see. And it all started with a surprisingly simple question.
I mean, it sounds so basic, doesn't it? For you and me, telling a cat from a dog is instant. We don't even think about it. But for a computer, this is one of the toughest problems out there. And for years, AI researchers had a very specific and honestly a very successful way of solving it.
And that solution was the Convolutional Neural Network, or CNN for short. For pretty much 30 years, if you wanted an AI to understand an image, you used a CNN, no question. They were the undisputed champs, inspired by the way our own brains process vision.
So what made these CNNs so good at their job? Well, think of it like this. A CNN works locally. It scans an image using these little filters, kind of like tiny magnifying glasses, looking for basic stuff like edges or colors or textures. Then it starts piecing those together into bigger shapes, and then finally into objects. It builds its understanding from the ground up. But then you have the challenger, the transformer, and its whole approach is completely different. It was built for language, and its specialty is understanding the relationships between all the parts of something at the same time.
The secret sauce for CNNs is this idea called inductive bias. You can think of it as a set of built-in cheat codes or assumptions. For example, a CNN just assumes that pixels that are close together are probably related, which makes sense, right? And it assumes that a cat is still a cat whether it's in the top left or the bottom right of the picture. These little head starts were absolutely crucial for making CNNs so good at understanding our visual world.
Okay, so while CNNs were the kings of computer vision, there was this totally separate revolution happening in a different corner of the AI world, the world of language.
And the absolute rock star of that revolution was the transformer. You've heard of the models it powers, things like BERT and GPT. They got so incredibly good at understanding and even generating human language that they just completely took over the entire field. And this is where things get really wild. Those researchers at Google looked at this master of language and asked a truly crazy question. What if we could take this thing that's designed to understand sentences and words and somehow teach it to see? I mean, that sounds nuts, doesn't it? An image and a sentence are just fundamentally different things. Or are they?
Well, this is where the genius of the paper really shines through. Their radical idea was to just stop treating an image like a grid of pixels. Instead, what if you could treat it like a sentence? And the process they came up with was almost ridiculously simple. First, you just chop the image up into a bunch of little 16 by 16 pixel squares. They call them patches. Then you just flatten each of those patches into a straight line of data. And then you just treat each of those flattened patches like a word. And you feed that whole sequence of image words right into a standard off-the-shelf transformer. No special vision-related tweaks.
Now you have to understand what a massive gamble this was. By doing this, they were throwing out all those helpful cheat codes, that inductive bias that made CNNs work. This new model, which they call the Vision Transformer, or VIT, had zero built-in knowledge about how an image works. It had to learn from total scratch that, the patch of a cat's ear is probably going to be above the patch of its eye.
And so they ran the experiments, and at first, it was a complete letdown. This is the part of the story where it looks like the crazy idea is about to fail.
So when they trained it on ImageNet, which is a pretty standard data set with about 1.3 million images, the Vision Transformer actually did worse than the state-of-the-art CNNs. Without those built-in assumptions, it just struggled to make sense of things with that amount of data.
So, was that it? Was this whole idea just a dead end? You'd think this was proof that, yeah, you really do need those specialized built-in features to teach an AI how to see.
Not quite, because the researchers knew something about transformers from all their work with language models. They knew it had a superpower.
And that superpower is that transformers are absolute data monsters. They might not have those clever built-in assumptions, but what they do have is this unbelievable ability to learn patterns from just massive, massive amounts of data. They just needed to feed the beast. And this slide right here, this is the turning point. When they pre-trained the vid on a massive internal data set with over 300 million images, everything changed. The Vision Transformer didn't just catch up to the CNNs, it blew right past them, setting a brand new state-of-the-art record.
And that led them to the single most important conclusion of the entire paper. This quote really says it all. We find that large-scale training trumps inductive bias. In other words, if you have enough data, you don't need the cheat codes.
A general model can just figure it all out on its own and do an even better job.
So how in the world does it actually work? How does a model that basically sees an image as a jumbled bag of puzzle pieces learn to understand what it's looking at so well?
The key is a mechanism called self-attention. For every single patch in the image, the model essentially asks, okay, how important are all the other patches to help me understand this patch? This lets it build this incredible map of relationships across the entire image. It learns that if it sees a patch that looks like a whisker, it should probably pay a lot more attention to the nearby patches that might look like a nose or an eye.
And here's the real game changer compared to a CNN. A vision transformer can have a global view from the very beginning. Right from the get-go, it can connect a patch of a tire at the bottom of an image with a patch of a windshield at the top and understand that they belong together as part of a car. It learns to see the whole forest, not just one tree at a time.
So you can see how this wasn't just some new, slightly better model. This paper kicked off a completely new era for AI vision. The impact was just immediate and absolutely massive.
And get this, it wasn't just about being more accurate. This table from the paper is mind-blowing. It shows that the biggest ViT model got better results than the best CNN, but it only took about a quarter of the computing power to pre-train. It was better, and it was cheaper to train at scale. That's just incredible.
So what's the big takeaway from all this? Well, the legacy of ViT is huge. First, it proved that one general architecture, the transformer, could be a master of completely different domains, like language and vision. It showed that just scaling up data could be more powerful than clever, specialized design. And of course, it completely opened the floodgates for research beyond CNNs, paving the way for the massive models we have today, like DALL-E and GPT-4, that can understand both text and images seamlessly.
This one paper really did change the entire direction of AI research. It taught a language model how to see. And in doing so, it left all of us with a really fascinating question for the future. If one single model can master both seeing and speaking, what's the next human skill it's going to learn?